This afternoon's talks are going to be in two parts. We have a scientific update from Dr. David Gamm about advances in research on therapies for retinitis pigmentosa and other inherited retinal disorders. And then Denise Jess and Vision Services staff from the Council will discuss adaptations in the meantime. And there will be a Q&A after the scientific part of the discussion, and there'll also be a Q&A after the Council part of the discussion. And I absolutely encourage you to chime in with your questions. So before I bring on Dr. Gamm, I want to bring on Denise Jess, who is the CEO and the Executive Director of the Wisconsin Council of the Blind and Visually Impaired. She's going to introduce the staff that will be on. Denise?
Yeah, Michael, thank you so much. Good afternoon, everybody. It is a delight to know that we had 90 people registered for this event, and we'll find out in the end how many came, and it's just really exciting. So we are so grateful that you have made the choice to spend a couple of hours with us this afternoon. I'm also absolutely delighted that we get this opportunity to partner.
Denise, we lost your connection. And so I believe she was about to say that we are very happy to be partnering with the McPherson Eye Research Institute to do this program. This is our first official partnership on an educational event like this, and hopefully there will be more in the future. Tonight there are 4 of us who are here, or 3 of us in addition to Denise, who will be here doing part of the second presentation. And I'm Jean Kelscher, and I am one of our vision rehabilitation teachers and also do education programming. Also here tonight is Brent Zenka, and Brent is a vision rehabilitation teacher with the council, vision rehabilitation therapist with the council. And Jim Denham is here tonight, and he is an access technology specialist with the council. So welcome everybody. And I'm sure Denise will be back in by the end. Okay.
Thank you. Thanks, Jean. I'm going to bring on right now, you can see Dave has already started to share his slides. So Dave Gamm is the director of the McPherson Eye Research Institute, and he's a professor in the Department of Ophthalmology and Visual Sciences at UW-Madison. And I think perhaps most importantly, his lab is at the forefront of developing photoreceptor replacement therapies for RP and other similar disorders, including AMD as well. So I'm going to turn it over to Dave.
Michael, before you turn it over to Denise, I'm back. My internet decided that was the moment it was going to crash. So I don't know if you had an opportunity to introduce or Jean introduced my staff. So it's a good thing I'm not easily flustered. So I'm back. So if you could just give me a quick update on where we are at. I just heard you introduce David.
Yep. Jean did a very nice job introducing people from the council. And I think we're about to go into Dave, but Denise, please feel free to say something if you'd like.
Yeah, no, I was just about ready to move into introductions of our staff. So Jean has done that. And let me just again say how grateful we are to have everyone here and to have this great opportunity to partner with you all at MERI. So David, please go ahead and roll, and I'll keep my fingers crossed to keep connected.
All right, good. Sorry, I was just going to say, Jean and Denise, you guys are unflappable. There was literally a 3-second break there, and Jean just moved right in, seamless as can be, and got everything done. So, well, thank you very much. Again, I can't reciprocate enough how pleased we are to be able to work with the Wisconsin Council of the Blind and Visually Impaired to put this together. What I really like about it is that it really combines what we're working on in the Institute to help folks for whom, there are no treatments or therapies available right now, or for the treatments that aren't where we want them to be, in comparison with, what is there available to you right now to make your life better and to maximize your ability to get around and do what you need to do in this world. And so I think that today's presentations will have a combination of the two. What can you do now, and what are we working on in the future to help you out? So and I know a lot of the folks on this call, and it's great to see all the friendly faces and to see new faces as well. Some of you may very well have been part of our summer research program, which was also virtual. And that one really encompassed all aspects of blinding disorders and what we work on in the McPherson Eye Research Institute. And of course, vision starts in the front of the eye and making sure you have clear corneas and clear lenses, and the light then hits the retina. The retina sends signals back to the brain, and then the brain does the actual business of seeing. And blindness can occur anywhere along that visual pathway. And we talked about different types of blindness from the front of the eye to the back of the brain back in the summer. But one particular disorder one type of disorder that we work on quite a bit here at the McPherson Eye Research Institute, and for which you are all on this call today, are retinal disorders. So we thought that it would be good to really focus in on retinal degenerative disorders, since such a large part of what we do here focuses on those particular disorders. And we have so many people that are friends of the Institute and are within the state of Wisconsin who have these types of disorders. So what I'm going to do today is focus in on retinitis pigmentosa and related degenerative diseases. But I'm going to start by kind of walking you through at a kind of medium level. I'm not going to be, I'm not going to be too high level, but I'm not going to get down into the weeds as well. But I want to really try and talk about what is retinitis pigmentosa. Why is it that one therapy isn't good enough for everybody? Why is it that there are so many different therapies that are being developed out there? What are the likelihoods that they'll come through and make meaningful improvements in patients' lives in the near future? And so to start with that, I'm going to be kind of have an educational component here, where I'm going to walk you through, what is the retina? How is the retina put together? And what is it that goes wrong in the retina that leads to loss of vision in retinitis pigmentosa? And that knowledge, I think, is really key fundamentally to understand why therapies need to be developed, why they aren't here already, and where we're going with them. So this is what I'm going to describe what I'm showing on the screen here too, but what I'm showing is a cross section of an eye. And the retina is a thin layer that lines the back of the eye like a wallpaper on your wall. Yeah. The central portion of the eye is filled with a clear jelly, so it's not as though it's hollow, but the retina is, again, this tissue that lines the entire back of the eye. Light passes through the front part of the eye, through the pupil, and then strikes the retina. Now, retinitis pigmentosa affects not the entire retina, but actually a very specific part of the retina. When we look through a dilated pupil, when you go to an ophthalmologist or an optometrist and they dilate your pupil and they look through there at your retina, this is what it looks like. It's quite beautiful actually to look at. It looks orange, but actually the retina itself is not orange. The retina is transparent like cellophane. Why it appears orange is because there's a lot of blood in a layer right behind the retina. And when that shines through, it gives us this orangish appearance. Right? Now, that's when you're looking at it through the pupil. But remember again that it's a wallpaper like in the back of the eye. But it's not it's thin, but it actually has a thickness to it. So if you take the retina out and you blow it up and you look at it under a microscope, you see that the retina is not just a plain old clear film, but actually a series of layers, a very intricate and complicated layer of different types of cells. And I'm showing them here by alternating layers of pink and darker blue dots. And what those pink and darker blue dots are different types of cells that communicate with one another like a circuit. And essentially, the retina has three wires, three different types of cells that connect to one another that start off our sense of vision. And deepest within the retina are the photoreceptors. And I have a black box here outlining where those photoreceptors are. They're actually deep within the retina. So the light has to penetrate the retina and go all the way to the bottom of the retina to hit the photoreceptors. And the photoreceptors, which are the rods and the cones, they are exquisitely designed to be light catchers. They catch photons of light in these structures called outer segments, which is the pink area within this box. And that's what starts, that's the pinnacle of vision. By catching those photons of light, the photoreceptors themselves are stimulated and they relay that signal to the next cell within the retina, and then the next cell within the retina, and then that cell sends signals all the way back to the brain. So as I mentioned just briefly now, photoreceptors come in two broad flavors. They come in cones and they come in rods. And cones have three different types, the red, green, and blue cones. Rods only have one type, just plain old rods. And really, as sighted individuals, we rely mostly during the daytime on cones. Cones give us our central vision. They allow us to see fine detail and allow us to see color. Rods, on the other hand, are more in the periphery of our vision, and they're responsible for seeing black and white, different shades of or different intensities of light, but do not contribute to our fine visual ability that we rely on most of the time to read, recognize spaces, and things like that. And the retina itself, there's even more complexity to it. So it's not homogeneous. All that wallpaper isn't the same, the pattern isn't the same everywhere on the wall. In the center of the wall is an area called the fovea, which is part of the macula. So you've heard that probably that term before, the macula. Just think of it as the central retina. And the central retina is where most of your cones are concentrated. So, and in the very center of it, there actually are no rods at all, just cones. And it's specially designed for us just in the center to be highly discriminating of detail and color. So I'm showing on this slide a larger area of the retina. You can see how different it is in the center. In the center, actually, there's only cones. That's all you have. All the other cell types have been pushed aside so that the light is not altered as it passes through and strikes those very, very important photoreceptors. I'm outlining the photoreceptors here. As you move away from the center of the retina towards the periphery, it gets thicker and thicker because all the other cell types, the second circuit, the third circuit, they're all pushed out a little bit further. So this is part of the reason why central vision and peripheral vision are different in terms of how they're affected in different types of retinitis pigmentosa. Okay, that's normal. So that's what retinas are supposed to look like. What happens during the course of retinitis pigmentosa? So over time, RP, and I'll call it RP as well, RP affects, for the most part, rods. And we'll talk a little bit more about that too. But let's just say photoreceptors in general. So on the far left of this slide, I'm showing a normal thickness of a retina with a nice, big, thick, healthy layer of photoreceptors. And they can be as thick as 12, 13 layers of cells, all sitting there ready to catch photons of light and to relay those signals back to the brain. But there's something amiss. There are errors in the programming in folks that have types of RP, such that those photoreceptors are not able to do their job for very long. And over time, they start to deteriorate. So if we look a little bit later on in the course of retinitis pigmentosa, we see the whole retina has thinned, but really the retina has only thinned because the photoreceptor portion of it has started to become discombobulated and thinner. During this period of when you're passing between a relatively healthy retina and a deteriorating retina, you'll notice that your vision will start to deteriorate as well, but you'll still have vision. It's just a matter of you kind of noticing that it's not quite the way it used to be. If the disease continues to progress, ultimately you have no photoreceptors at all. And once the photoreceptors are gone, there's nothing there to initiate vision. So the lack of that vision catcher or that light catcher means that that the rest of your system has no input to it. And then if you go even later in the process, even the remaining retina that's there will start to get thin and start to get a little disorganized. So out of, say, disuse. So what does this look like to a person who has RP? I'm showing a picture of the Monona Terrace. And so early on, one might notice changes almost like a jigsaw puzzle with loss of vision in the periphery. But that central portion is maintained for most folks with RP. Unfortunately, in many cases, even that central portion, those cones, are also affected at a much slower rate, such that even though you hold on to that kind of tunnel vision, that central vision, over time, even that central vision is threatened, and you can lose that as well. It's also important to know when I talk about retinitis pigmentosa, it's not one disease. So it's sort of like saying arthritis or cancer or things like that. It's a broad term, but it actually encompasses many, many different diseases that are all kind of lumped together with one umbrella concept. So there's different types of arthritis too. There's rheumatoid, juvenile, psoriatic, so on and so forth. And they're all different diseases within that one umbrella. Many decades ago, before we had the ability to test genetics and genes, physicians lumped it together because it all kind of looked the same. So they called it one thing. But starting in about 1990, when people were able to actually look at the genetics of retinitis pigmentosa, we started to see that it's not caused by one thing, but actually caused by now over 270 different genes that can be mutated that can cause loss of vision under the moniker of retinitis pigmentosa or RP. And that's still going up. That's 2018 that I'm showing right here. So you can see that our ability to find the cause of RP has gone up precipitously. Unfortunately, what we found is that it's many, many different things. And that makes it more complex to address from a therapeutic standpoint. So when we break down what those genes are in sort of a pie chart, you get into these little tiny slivers. So worldwide, about 2 to 3 million people have RP. And you cut that pie up into 270 different slices. They're not all the same slices, but you cut that up and you can see in some cases, there may only be a handful of families worldwide that have that particular gene mutated causing that type of RP. Other types are much more common, and they're regionally more common in certain areas too. You'll see a lot of a certain type, say in Eastern Europe or in Scandinavia, and another type in Japan. And that has to do with the way genes segregate. But as you can see, it's a daunting list. There are a lot of different genes that can cause retinitis pigmentosa. And that can make people feel like they're relatively alone in the universe, because it's like not only, I mean, I have RP, but I have this type of RP, and I don't know anybody else that has this type of RP. So who's interested in helping me out? And I can tell you that a lot of people are, and for different reasons, and there's different approaches, some of which really pay attention to the gene and the mutation, and some of which really don't care. It doesn't really matter what type of mutation or gene that is affected in your family. And I'll talk about that next. It's also, I don't want to leave other people out, because we oftentimes use RP or retinitis pigmentosa as a catch-all term. But in actuality, RP refers to diseases that attack the rods first, which lead to peripheral vision loss, and then secondary central vision loss. And RP is a type of a broader category called an inherited retinal disease, kind of runs in families or is passed along through your genes. And so RP is one of those, and the most common, and it causes peripheral vision loss that eventually affects your central vision. Another type are called inherited macular degenerations. Now, this is not age-related macular degeneration. That's a subject for a whole different virtual seminar later on. But inherited macular degenerations are ones where it's a genetic defect that is passed along, but it affects the central vision because the macula is the center of your retina. And so if the disease only affects the center of your retina, you lose central vision, but it maintains, for the most part, the periphery. And examples of that would be Stargardt disease and Best disease. These are actually quite common. Stargardt is actually a very, very common disorder, relatively speaking. And they see the reverse. They see loss of central vision, but relative preservation of peripheral vision. That wouldn't be considered RP, but it would be considered an inherited retinal degeneration. Then you have a rarer group of disorders called cone rod disorders. And as the name suggests, it affects both cones and rods relatively simultaneously. So it affects both the periphery and the central vision together. And then lastly, you might hear the term Leber congenital amaurosis, which is another category of inherited retinal disease or genetic disorder leading to blindness. And LCA is any combination of what I just talked about. So whether it be RP or cone-rod disorders or inherited macular disorders, but it's severe and very, very early in life, generally affecting infants or children, as opposed to later in life. So you may hear the term LCA or Leber congenital amaurosis. But in terms of therapeutic development, all of them are important to you because each one of them, the goal is to be able to either fix or replace the gene defect. And those are relatively broadly applicable technologies, or replace the cells, the photoreceptors, once they're lost during the course of disease. And that is agnostic. That can help everyone. Okay, so getting to the treatment approaches, that's sort of the background a little bit. So now let's get into what are the different treatments that are being worked on out there, both at the McPherson Eye Research Institute here at UW-Madison, as well as around the world and our collaborators around the world as well. So again, we have to think about the transition between a healthy retina to one that's losing photoreceptors, but there are still photoreceptors around to initiate vision. And then when there's no photoreceptors, so there's complete blindness or near complete blindness. And so we have to separate out where you are in that continuum of the disease process to determine what is most applicable in terms of a potential therapeutic. So early on, gene therapy is most appropriate when you still have vision, the photoreceptors are still there. And that's because genes only work when they're inside of a cell. If there's no cell, then the gene has nothing to do. It just sits around there and it can't do anything. So you have to have some cells that are still alive and kicking in order for gene therapy to be effective. Once the cells are gone, then you have two choices. You can either try to replace the whole cell, that's cell therapy, and we'll talk about that. We pioneer that here at the University of Wisconsin through the MERI, or a technique called optogenetics, which I'm going to touch on very briefly at the end. And optogenetics is a way to say, well, to heck with photoreceptors, let's try to make the cells that are still there behave like photoreceptors. And I'll get to that at the very end. So I'm going to cut it up into two different sections. The first one will be gene therapy. And this actually is the most difficult to wrap your head around because it can get complicated really quickly. But you hear so much about it that I really want to try and give you a kind of a scientific American course on gene therapy and why some are better for some types of RP and others are not. So what are the considerations? When we just throw out the word gene therapy, what does that mean? Does that mean one size fits all? No. Unfortunately, the downside of gene therapy is A, you have to have a lot of some cells still remaining that are alive. So you can't be too late. You can't miss the bus. And secondly, they're very customized. Each one of them is specific to a particular gene, and in some cases, a particular mutation within a gene. Okay, what does that mean? So there's two things that that are the primary considerations when it comes to gene therapy. Oh, I should also mention too, that for the purposes, really for practical purposes, no one's going to treat you when your retina is perfectly healthy. The risk is too high to go in there and do a surgery and give you an experimental therapy when you still have excellent vision. So really the sweet spot for gene therapy is when you've started to lose vision, but you still have some left. Okay, so what are the considerations? The two main ones are, what is the gene that's affected? And I showed you there's 270 of them, right? There's a lot of them. And then secondly, within that gene, what is the type of mutation that made that gene not work? And I'll get into each one of those now. But first, I got to tell you a little bit about genes. So gene therapy, genetics, genetic disorder doesn't really help you too much unless you understand what a gene is. So you have cells. Your body is made up of trillions and trillions of cells. Each one of those cells has a nucleus, and within that nucleus is all of the genetic information for your entire body. So the blueprint for your entire body is in every one of the cells, every one of the nuclei of every one of your cells. Now that particular cell may only use a fraction of the blueprint there, just so that it can do its job. A photoreceptor doesn't have to do the job of a liver cell. So there are genes and parts of that, of the chromosomes and the DNA that are important for liver cells, but not photoreceptor cells. So photoreceptors turn off the liver cell stuff and turn on the photoreceptor stuff, and vice versa. So even though all of the genetic equipment is there for every cell to do all the jobs, they know which jobs they have to do, and they shut off the stuff they don't need, and they turn on the stuff that they do. So all of that DNA that you have, all of that blueprint is incorporated in chromosomes. And there are 23 pairs of chromosomes in each one of your nuclei. And those chromosomes are just condensations and wrapped up millions and millions and millions and millions of bits of information in DNA. Okay, so you have, and all the different chromosomes have different sizes, and they contain different amounts of DNA. And that DNA, if you think of it like a string of zeros and ones, like encoding for a computer. And a lot of that DNA doesn't do much. It's kind of like a desert wasteland that we don't understand too well. But interspersed are oases of genes. And what the genes do is they code for proteins. So you have these gene blueprints that are interspersed on your DNA within chromosomes. And those genes say, okay, we need to make certain parts in this cell. This cell needs to have a muffler, it needs to have a spark plug, it needs to have tires. And so I am the gene that's going to tell you how to make a tire. And I'm the gene that's going to tell you how to make a steering wheel. And you need each one of those genes to do their job and to instruct how to make those parts in order for the car to run. In this case, in the analogy, the car is the cell. You'll see I'll use cars as my main analogy throughout this entire talk. So those parts, those proteins, you can remember because protein starts with P, part starts with P. Those proteins are parts that are coded by the genes. Then those proteins are made and they help the cell do their job. If there is a hiccup, if there is something wrong with that code in that gene, then the protein is either not made at all or it's made wrong. And when that happens, it disrupts the whole cell. And then the cell can't do its job. Just like if you have a car with no steering wheel, you're going to run into the railing. If you have a car with no wheels, it's not going to go anywhere. So every one of those parts have a role to play, and it can disrupt the cell. And depending upon how important that part is, it tells you how fast you're going to lose your vision, or how important that is. So if it's kind of important but not terribly important, then it may take decades to lose vision. If it's a super important part, like a piston, then you may be blind from birth. So that's where you get the different types of effects from one mutation to another. Okay, so that's what is your gene. So you need to know what gene you have or what gene is disrupted, because that tells you what part is not working correctly. But that's not enough, because there's a lot of different ways that you can make a gene not work correctly. And each one of those different ways has different therapeutic approaches. So there are different labs, different researchers, different companies that are working on ways to overcome different types of mutations or errors in these genes. And so what different types are there? There's no quiz, so don't worry about memorizing, but it's just a matter of letting you know the different types. So there are situations where a part of that code is switched out and the wrong instruction is placed, okay? In that case, the protein or the part is made, but there's something wrong within that part. There's also what we call insertions, where a wrong thing is inserted into the code such that there's a random piece of steel just in the middle of the part. There are also deletions where parts of the code are removed randomly such that there are critical parts of the part that are no longer there. And then lastly, there are things called nonsense mutations, which essentially cause the part to stop production. So it gets about halfway through, and then it no longer makes the other half of it. Okay. Now, the reason why I bring all this up is because each one of these different types of errors within the gene has different potential approaches for fixing them. Okay, now there is a third consideration. So the first consideration is what gene is it? The second is what is the type of mutation that's causing the gene to be malfunctioning? And then lastly, is it a dominant or a recessive gene? How is it inherited? So dominant genes, well, first of all, to start with, you should know that all genes come in pairs. So you have a backup. So every one of those genes that I showed you before that makes a product or a part, each cell has 2 copies of those. Okay? And in dominant diseases, these are mutations that if they're inserted into the gene, then they cause the whole thing to go awry. So only one of the 2 genes needs to be malfunctioning to screw up the whole system. Whereas recessive genes need both of the genes to be mutated in order for it to cause vision loss. As it turns out, the dominant diseases are harder to fix because in recessive diseases, essentially, there is no protein. It doesn't get made or it doesn't work. And so in those cases, you have to come in with new genes to replace the ones that aren't working. But in dominant diseases, you have a bad actor. You have a gene making something that's actively making a problem. So there you have to, in most cases, remove the influence of the bad gene. You can't just add more good gene to it. You have to actually remove the bad gene. You can think of it like an orchestra. If you have an orchestra and you're missing the percussion, then you notice that, and the music isn't right. And you need to go out and hire some new percussionists. However, if you've got a bad percussionist and he's just slamming on everything you possibly can slam on, then adding a good percussionist isn't going to help unless you shut up the one that's doing the bad job, because all you're going to hear is the one that's clanging on the instruments willy-nilly. So that's the difference. Is one you have to replace and remove. You have to fire them and hire. One you just have to hire. So 3 things then. And so when you're talking to your ophthalmologist or you're talking to or you're perusing the latest research, pay attention to what gene they're talking about, what type of mutation they're talking about, and whether or not it's a dominant or a recessive disorder, because it all matters. So I told you I'd have a car analogy. I don't give a talk without a car analogy. So if you think of a cell, so I'm going to recap this a little bit by using this analogy. So if you think of a cell like your photoreceptor, so as a Corvette, because I think photoreceptors are the coolest cell in the body. So if you think of a photoreceptor like a Corvette, that Corvette has lots and lots of different parts. Okay. So, and like I said before, each one of those parts is necessary for that car to run. It may still look like a car. It may still, you can still sit in it, but it is not going to run without every one of those parts and every one of those parts being in the right place and working together as a team. And each one of these parts then would be like a gene or a protein made by a gene. Now, if one of them is not correct, so it has a mutation in it, then your options are to either add a new part, remove the bad part, or fix the part altogether right where it sits. So go in there and fix it. Don't take it out. Don't put a new one in. Just try and fix it where it lies. And adding a gene is essentially putting in a whole new gene. Removing a gene is like going in and trying to selectively deactivate the bad gene that's causing problems, the percussionist that doesn't know what he or she is doing. And then fixing is repairing it. So you're not adding it, not subtracting it, but rather repairing it. And in terms of where the technology is now, adding genes is much more advanced than removing, which is more advanced than fixing. So depending upon what your gene and what your mutation is, you may be in one of these buckets. And the way what's out there right now in terms of gene therapies, where we're most advanced is on that addition of genes side of things, as opposed to the fixing. There's work being done in every one of these buckets, but they're at different levels in terms of the race. There are different advancements. So another thing to talk about, so if we just talk about adding genes now, so if we're just going to say, hey, there are no spark plugs. I'm going to go put in more spark plugs. The thing to consider there is, how do we do that? I mean, how do you go and put a new gene into millions of cells selectively? I mean, you can't just inject them like you would inject your arm or something, right? What we use are things called vectors. And the McPherson ERI calendar and annual report, by the way, will be all about how we deliver genes, how we deliver therapeutics to the retina. So hopefully you'll get that and you'll be able to read up more about it. So we package these new genes or whatever therapeutic or gene therapy we want into either viral particles, which sound like, oh, during the middle of COVID, you're like, oh my goodness, you're going to give the viruses. But these are specially designed viruses that don't have the ability to cause disease, but are able to hone in on certain cells and deliver genes. And so we commandeer essentially biology and nature to do this. The problem is that these vectors, these packages that we put together, are limited in what they can carry. So the box that we can put the part in has a certain size to it. So if your part is too big for the box, right now, we don't have anything for you. But that's one of the things we're working on in the McPherson ERI is we've got bigger and bigger boxes so that we can package bigger and bigger genes, bigger and bigger parts, so that more people can benefit from gene addition therapy. So right now, small box. So only the small genes can be potentially fixed that can require addition. Big genes need bigger boxes. And so that's an important area of research that we're doing right now. A lot of it through our engineering colleagues here at the University of Wisconsin through the Institute. So that brings us then to what are the trials we have now. Here's a list of trials that have been either performed or are active to date for retinitis pigmentosa and inherited retinal degenerative diseases. These include a couple of genes for LCA, RP65, which is Luxturna. You maybe have heard of that. That's the only FDA approved one. CEP290, there was a Stargardt disease one. Choroideremia has actually 3 going on. Achromatopsia, Usher syndrome, and a couple of X-linked disorders. In total, however, you think, okay, well, these guys are so lucky. They have clinical trials. Well, they're still relatively early on. And if you look worldwide, less than 200 eyes have been treated thus far in these clinical trials. Okay, so it's not like there's thousands and hundreds of thousands of people out there that are getting their gene therapy and you haven't, right? It's still in that phase where they're working out the safety, making sure that they're not harming patients. And it's on the cusp of these certain genes to be taken off and to be offered to more patients with them. But they're limited to the genes and then sometimes the mutations that they're made for. So these are smart bombs. These are not things that can be broadly applied to a lot of different folks. Okay, I'm now going to move on to cell therapy. So we had gene therapy. Now we're going to talk about cell therapy. This is later on in the disease where gene therapies are no longer going to help you because, again, the car is not there. So the parts don't matter anymore because the car itself isn't doing too hot. So it's completely gone. It's either destroyed to the point where throwing a spark plug into this rusted heap is not going to help this car run, right? And in fact, many times, there's not even a car there to begin with. It's not only just broken down, it's not even there. So you no longer care about the gene. You no longer care about the mutation. You don't even care if it's dominant or recessive. You just want a whole new cell in there. So how do we do that? Well, there's a couple of different sources of new parts or new cells for the retina. And those are embryonic stem cells and induced pluripotent stem cells. Embryonic stem cells are derived from the Bush lines that were developed at Wisconsin many, many years ago in the late 90s. iPS cells are derived from blood or skin of individuals walking the planet all the time. So we have options of using either one of those. And this is homegrown. This was made in Wisconsin. So human stem cell technology was born at the University of Wisconsin-Madison, and we continue to be the world leader in this area. And what we did in my lab and through the McPherson Eye Research Institute is we took that technology and used it to direct these stem cells specifically to make not just human retinal cells, but actually human retina. And we can do this in a dish, and we can do this in a highly scalable manner such that we could treat entire cities if the technology works. So I'm showing here a very magnified view. Each one of these kind of golden Cheerios that are these mini retinas are about the size of a big head of a pin. But if we look at them over time, eventually what we see is that they will make all those photoreceptors in those beautiful layers. They'll make the cones, they'll make the rods. And those cones and rods can detect light. They can transmit signals to other cells within those tiny, what we call organoids. So it's remarkable that we can take something that starts as a blood sample, like you might give for a cholesterol check. And at the end of a while, it takes a good number of months, but after a certain period of time, we have in a dish an unlimited supply of photoreceptors, light-sensitive cones and rods. That's great, but can we actually use that to help people? And so that allowed us, and this is where I have to say, disclose the fact that I'm a co-founder and the chief scientific officer of Opsis Therapeutics here in Madison. And this was a company that was an offshoot or started through the university to take this technology and bring it to patients. I think a lot of folks have heard me talk about this. And this just shows you, I showed you all those little golden Cheerios. In Opsis, and Nick Manousos, who's the CEO of Opsis, who's on this call, on this webinar, will recognize this. But what Opsis was able to do with their crack team was take the technology that we developed through the Institute and in my lab and scale this up to the point where we can have, these are like 2 liters. These are like 2-liter bottles of billions and billions of photoreceptors that are all made in a very precise, very safe manner and are applicable then, we hope in the near future, to clinical use. So really remarkable to be able to take something that is made in a very customized way and scale it up to the point where it can hopefully also be economically applied to patients. We're not the only ones. Riken in Japan has a program that's also looking to replace photoreceptors. And you might also, from a cell therapy standpoint, have heard about J-site or Renuron. The reason I put them in parentheses is they don't use pluripotent stem cells. They use human fetal cells, and they really don't replace photoreceptors. They put them, the idea there is that they're elaborating factors and things that help your photoreceptors that are already there. So they're, even though they're, quote, cell therapies, they're not cell replacement therapies, but you might hear about them, so I put that there. All right. And in collaboration with Opsis, what we're looking for going down the line, one of the nice things about Opsis being a uniquely Wisconsin venture is that we look to partner with the Department of Ophthalmology and Visual Science here at UW to have this be one of our clinical sites. So we're hoping very much to have Wisconsin be at the forefront of testing this therapy. Okay, so I'll finish up here with a discussion of optogenetics. So what is optogenetics? So as I mentioned before, it's the question, okay, the photoreceptors are gone, gene therapy isn't going to work. Let's make what's still remaining respond to light. Now, normally those cells don't. The cells that are still, the second circuit and the third circuit, they're not designed to detect light, so they don't know how to do it. But can you insert parts that will allow them to detect light? And that actually shows some promise. It's sort of like taking a bathtub and saying, I want to make a car out of it. So if I stick wheels on it in an engine, will it work? So to the extent that optogenetics can give you something, it may take you a long time to get to the quick trip, but maybe, just maybe, it can help you in some respects. So it's trying to bypass the system. All right, so that's kind of where we're at with regard to, what is RP, what are the considerations that we have as clinicians and researchers, what are the types of therapies that we're developing here at the McPherson Eye Research Institute. So why does it take so long? And I've shown this picture, I think, a number of years back in one of our summer research seminars. And the reason for this is not because there's some evil person at the FDA who doesn't want to help folks, but rather these are experimental. And it's possible to hurt people along the way if we're not careful. We have to first do no harm. And it takes a while to go from an idea to getting the funding for it, I mean, do we have the money to actually do the research, to being successful with your idea? And a lot of ideas don't work. And then getting a sponsor who will then put in the big bucks to be able to move it to the next stage, which is clinical trial and FDA approval. So it takes a long time, and it's a circuitous route. Is that something that's good? Well, I tell you that to some degree, it's never fast enough, but there's safety built in. And my analogy for this is the Cooper's Hill cheese rolling race. So those of you who heard this analogy before, I apologize, but this is a race that's put on every year in Gloucester, England. And essentially what they do is they take a really expensive big wheel of cheese and they roll it down a steep mountain. And whoever catches it first gets to keep the cheese. All right, so as you might imagine, people going hell-bent down a steep mountain going after a wheel of cheese is a pretty chaotic thing. So if we were just allowed willy-nilly to just make whatever we had in our head and throw it into patients, this is kind of what those clinical trials would look like. And somebody might get lucky and might get that cheese. But most folks are going to end up like this. So you have to be, which is injured. So there's going to be a lot of injuries along the way. And it just takes one injury to put the kibosh on the entire operation and set everybody back a decade. So we don't want mavericks. We don't want cowboys out there promising the world and throwing everything in the kitchen sink in people's eyes, because it hurts the folks that are doing honest, iterative, well-meaning work. The eye is leading the way, though. I can tell you that almost any other system in the body, whether it be diabetes in the pancreas, liver, anywhere else, they are envious of what's going on in the eye, because almost every company has their leading therapeutics to treat RP or RP-like disorders, because there are so many things that are advantageous about working with the eyes, not the least of which is you got two of them, and they're not in the middle of your body. And we can dilate and look at what's going on without having to put you in an MRI scanner. And the eyeball is relatively sequestered from the rest of your body. So if something goes wrong, it's not going to leak into your brain or into your liver and kill you. So there's lots of things, lots of reasons why companies who aren't even necessarily interested in RP still want to go after RP first with their therapeutics as a gateway to going to, say, the next disease, something else. So we do have to have realistic expectations. We're not going to hit a grand slam home run right out of the gate. Like any technology, it's going to take time to get better over time. So just like, again, cars, there's a lot of difference between the cars we have now that can drive themselves and the cars we had to crank way back when they were first invented. So there are going to be improvements over time, but we're not going to erase the vestiges of RP right off the bat. And in the meantime, be very aware of snake oil salesmen. There are all kinds of presumably legitimate companies who will prey on people who are desperate and promise them the world for a steep price, and they have no potential to really help you. So lean on us, lean on your physicians, make sure you're getting advice, good advice, honest opinions, and make sure that you look out for yourselves and your family. So thank you very much. I know I went over, but I hopefully that was educational for you, and I'm happy to answer any questions. And I'll stay on late too after the Wisconsin Council presentation to answer any questions you may have too.
Thank you, Dave. You can stop sharing your screen now. And what we're going to do is right now we're going to take about 10 to 15 minutes of questions that people have right away. And we have a couple of people who asked questions before when they registered as well. And Dave will be able to answer those. And as he said, he'll stay on afterwards. And then we do want to start with the council section of the presentation as well. And after that, we'll have probably a somewhat longer Q&A, and we encourage you to stay on. I'm going to start with a couple of questions that people asked when they registered. And there were a number that I think that Dave covered, including is there a cure for RP, and talk about experimental RP therapies that are going on. Dave, we had a couple of people who asked about Usher syndrome.
Yeah, so again, in these lumpers and splitters, so you have RP, and we already know that RP has 270 different gene mutations. Usher syndrome is a group of genetic disorders within RP that affects both the photoreceptors as well as the cochlear hair cells. So there's a deafness component of it as well. But Usher syndrome actually isn't one disease either. Usher is actually more than 10 different genes, and there's different types. There's an Usher 1, an Usher 2, an Usher 3. It's actually an Usher 2A, B, and C, and so on and so forth. So Usher syndrome is a prime example of how knowing your gene and knowing your mutation is important. For instance, Usher 2C is one of the biggest genes known in the body. It is not fitting in any of the cardboard boxes that we can make right now. So adding it back is really not an option. However, fixing the mutations is a potential option, and we're working on that right now. So that's different than somebody who say has MYO7A or USH1B or USH2A. Some of them are small enough to be gene additions. Some of them require fixing. Some of them require knocking out the bad gene. When you say, what about Usher syndrome? Again, my next question is always going to be, well, which Usher syndrome? What's your actual gene? And this gets back to getting a genetic diagnosis when you can. And we have that at University of Wisconsin-Madison, Department of Ophthalmology. We have genetic testing. There's other areas around the world. It used to be really hard to get genetic testing and to convince insurance companies to pay for it. There are avenues now, and it's increasingly easier to do. Not saying it's always going to be completely covered, but it's really important. But about a third of patients with RP, which include Ushers and all these other ones, you'll do this gene testing and it'll come back inconclusive, or they won't find it. We're doing something for those folks too. We recently published a paper just this year where we took a family, and it was a family from Boston, and they had 2 girls who were born blind. And they did gene testing, and they couldn't find out a single reason why the children were born blind, but they knew it was genetic. And they had a son who wasn't blind. And so they did a complete genetic workup, and then they asked us to make pluripotent stem cells, iPS cells, from blood samples from each one of those children and make their retinas in a dish. So we did that. So we essentially made the children's retinas in an unlimited supply in a dish here at UW-Madison. And then we tested the retinas that we made in the lab, and we found the genetic defect that they had. And it turned out to be a very odd mutation in a gene that's already in clinical trial. So it was really rewarding to be able to take a family who didn't know what their gene mutation was and actually say, not only do we know what it is, but it happens to be one of the ones that has a clinical trial and a potential therapy on the horizon.
So I see that we have a couple questions coming in, but I did want to say to please feel free to ask any question. I'm an English major, and when I first started working for the Institute, my reaction at the end of most seminars would just be, can you please repeat that? So my point is that there is no question that is too simple, and if you have it, somebody else is going to have it as well. So please feel free to ask anything. And Dave, I'm going to go with a question that is on the chat now. What is the biggest hurdle facing your research? You mentioned there are so many factors, but you've also showed containers of photoreceptors, leading me to assume you've figured out how to manipulate the cells. So is it the vectors or something else that is the biggest issue right now?
Again, it depends on, again, the buckets. So the biggest is there's big issues with gene therapy, and then there's the issues with cell therapy. So with gene therapy, it's delivery is a big one. So right now just a few of these genes can be delivered and get to the right place where they can do their job. So can we make better containers, more efficient containers? And then also the gene therapies themselves, their efficiency is not great. So you may only fix 1 out of 100 cells. And the cells that you fix may be only 50% fixed. So while the proof of concept is there, that we can do it, it has to make it better, we have to improve efficiencies and things like that. So, iterative improvements. So a lot of things on the gene therapy end of things. On the cell therapy end of things, we're quite good at part manufacture. So we can make authentic parts. What is harder to control is what's left and how will the retina that's there, the retina that has RP, how will it interface? Will it shake hands with those new cells, right? New wine into old wineskins, so that interface, making them connect so that they will talk to the cells that are still there in the patient. Right now, that's a kind of a random event. There's nothing that we can do to facilitate that. We're relying on the good faith of the retina of the patient to reach out and do that. And to some extent, it will happen, but again, not so efficiently. So we're also working, and we have projects now with the Department of Defense to develop scaffolds or patches that will take those cells and make them a particular orientation, because in reality, they're supposed to be kind of lined up like tin soldiers. I mean, it's very exquisite, right? So can we embed those into kind of a patch, a bioengineered patch, so that they have a better opportunity to be oriented properly and to communicate and do those handshakes. So those are, and that costs money, and oftentimes costs a significant amount of money, and it takes time. We don't snap our fingers on those things.
Next question, is all RP hereditary?
Technically, yes. Yes, it is. It may not run in families because recessive disorders, so a couple things. It can be spontaneous. So a genetic mutation can just spontaneously occur. It's called a founder. So just because you look back and you go, well, nobody else in my family has this, how do I have it? There's two ways that can happen. One is that and the most common is that it's what's called the recessive disorder, which means that it takes two bad copies to cause the problem. And one parent has one bad copy and the other parent has the other bad copy. And then you got both of them, when they came together when you were born. And so your parents don't have it because they have one good copy still, and you need two bad ones to have the disease be caused. And so 25% chance, recombination just happens. The other possibility is that it's a spontaneous mutation that occurs in a sperm or an egg, and it was just in that particular cell. And so essentially the genetic problem started with that particular person. So there's no history of it. But all of that is genetic, yes.
Okay, next question. My 17-year-old son was diagnosed with RP and a CLN3 genetic mutation. Are there any therapies, trials, studies happening with CLN3? And I guess maybe this would be a good opportunity
CLN3.
to talk about where people could find out if their particular mutation is being worked on.
Yeah, so there's tons of different types of obviously 270 different types of ones, and almost every one of them has somebody probably working on that one somewhere. I don't know everybody that's working on everything and every particular gene, but like I said, you don't need to have your particular gene worked on for a lot of these. So for instance, a lot of cell therapies and optogenetics and things like that, there are that doesn't care what your gene is or what your mutation is. That's why we've gravitated more towards that type of a therapy, because we don't want RPE65. So the RPE65 Luxturna gene therapy, which is FDA approved, took 20 years to make and over $40 million. And there are probably 3,000 people worldwide that have that disease. So, that's a lot of money per patient and not necessarily sustainable. So there's a lot of effort to look at therapies that are more agnostic towards the actual type of gene. So I understand that the first question is, what about mine? And it's always good to have folks looking for specific therapies for your particular disorder, because it gives you one more shot on goal. But you don't have, just because somebody isn't actively moving a therapy for that gene forward, does not mean that there are not active products being made. Case in point, the reason I listed those different types of mutations, for mutations that cause a stop in the production of a part, with the nonsense mutation that I mentioned, the last one on that list, those generally are amenable to what are called read-through drugs. or read through therapeutics. In that case, they don't really care what gene that nonsense mutation is. It will read through that and make a normal protein at some level of efficiency. So again, there's an example where, you ask, what is my gene, and is there anything going on with my gene? The next question is, what is the exact type of mutation? Because there may be things going on that will treat my mutation regardless of what gene it is. Okay, so long answer for nobody that I know of for CLRN3. Clarin1, and these all come in different things. There's a CLRN1, and I know people are working on that. But it doesn't mean that you're out of luck.
I want to note that Jenny from the Department of Ophthalmology noted in the chat that clinicaltrials.gov is an excellent source to find out what is being worked on worldwide. So that's clinicaltrials.gov.
Yes, but be careful. There are some clinical trials listed on clinicaltrials.gov that are very much disputed by mainstream scientists and are felt to be essentially shysters. So that's a good place to peruse, but your first phone call should not be directly to the people necessarily saying it. Talk to somebody who's not directly involved in it, right? Get some advice from people who don't have skin in the game, who don't have a conflict of interest. For instance, there's a stem cell group in Florida called MD Stem Cells. They have hurt tons of patients. They put fat into the middle of your eye and tell you that it's stem cells. They have blinded people. They are listed on clinicaltrials.gov. Okay, and so I was part of a task force to try and root out these folks, but it's hard with all the lawyers involved. So again, great place to go, but get somebody you trust to give you advice on these as well.
That's a good caution. We have 2 or 3 minutes before we move on to the council part, but I did see that Rosemary raised her hand. Rosemary,
Hi.
Unmuted if you want to ask your question.
I do. Hi there, Dr. Gam.
Hi.
I was wondering, on behalf of my daughter and myself, because she inherited my RP, we both have been, our blood has been researched in autosomal dominant RP.
Yeah.
I can't remember the specific number.
Probably
I know
rhodopsin. Was it a rhodopsin mutation?
Yes.
Rho, yeah.
Yeah.
Very common.
Yeah, and I know that the lab that researched it was in Texas at the time, years ago. But I was wondering now, how do they exactly tell? I mean, both of us have some usable vision in the middle. We're both still visual artists. We met you.
Yes.
Yeah, Dr. Stepien, yeah. And, so it's like with me, my looking through the paper tube is smaller. I have like about 5 degrees, where she has about 15 degrees.
Mm-hmm.
And my right eye is starting to get a little distorted, kind of like an hourglass distortion. But we still can see. And the thing is, how do we figure, like, if we were to be up and okay to be a part of this trial for the first portion, that still have some vision versus those that don't, how do they determine like how much you have left? Do they do it in degrees of vision, or do they do some other way?
60 seconds, Dave.
What?
60 seconds.
Oh, come on. I can't say my name in 60 seconds.
Sorry.
Tremendous number of excellent questions all in there. First of all, for rhodopsin, there is a group, William Beltran at the University of Pennsylvania, a collaborator of us at the McPherson Eye Research Institute, working on that disorder, and it looks quite promising. It's also one of the ones that would benefit from cell therapy. But the question is again, meeting you where you are at. You still have usable, important vision, right? So there are therapies being developed to help preserve what you have left. So it wouldn't give you anything back, but there are therapies, gene therapies, that are designed to say, how do we keep folks that have remaining central vision from losing what they have? Mm-hmm. So I didn't even talk about that because again, they don't want to give me that much floor. But so there are things along those lines that are really important. How do we determine that? That's where one of the reasons why everybody loves the eye. We have 1,000 ways to Sunday to be able to exquisitely document what's working and what's not in your retina, both by having you do studies and by doing things like optical coherence tomography, adaptive optics, imaging. We have engineers at the McPherson Eye Research Institute that are developing new ways of being able to just dilate your eye, look inside there, and look at individual photoreceptors and hopefully determine which ones are working and which ones aren't. Doing that while you're sitting there, perfectly happy, eating a cookie. So, you know, not putting you into a scanner, not having to take an eye out or anything like that. So that is one of the great benefits of having an eye-based disorder, is that we have a plethora of tools that will allow us to hopefully categorize you and tell you what's best for you at your stage of disease.
Okay, so we are going to come back to
Thanks.
question and answer after the council section of this, and which I have been very excited about hearing, because I have not heard this before. So I do know that we have a couple of questions still in the chat and a couple of questions that were asked in advance. So we'll hear both scientific and questions on adaptation after the council's presentation. So I'm going to turn this over now to Denise.
Actually, I did.
Jean, I'm sorry. Jean,
That's all right.
go ahead.
Lots of good questions, and so please continue to put those in the chat, and we can take them. Dr. Dam is going to hang around until we're done tonight, and so put them in the chat, and you can also put questions to our team in the chat as we talk about technology. And again, no question is too basic, or you know, you don't know enough technology or whatever, because there's so much of it out there. Never think that way when somebody's talking to you about technology, because what I know is not the same as what Jim knows or what Brent knows. So Jim, Brent, and I are going to talk about different technologies that might be helpful to you along this journey of vision change. And so we're not going to go into detail. We're going to stay not outside the weeds, and we'll be giving broad suggestions. And we'd be happy to respond by phone or email to inquiries about technology or training at any time after. And just to let you all know, I will be sending out a handout, probably tomorrow, that will list all of the technologies and their websites, so that you'll have an opportunity to go do some exploration of those sites on your own, where you can get more information. The handout will also list places in Wisconsin who offer services, vision rehabilitation and assistive technology services for people. So do look for that, where you can get more information. And we were going to do a breakout session or a breakout room activity, but I'm kind of thinking that maybe just to say a few words about eye health. You've been at it an hour sitting there staring at your screen. And so you might want to, just to give your eyes a little break, is over the next few minutes, just look at the wall, the opposite side of your room, so that you're getting in some good distance viewing, and just look around, take your time, let your eyes use something besides that computer vision to do that, and feel free to get up and take a stretch break. There is nothing wrong with doing that while we're doing the presentation. You all can still hear what we're saying. Doesn't matter if you're sitting in a chair or if you're standing next to your chair. So if you just need to stretch because you have been sitting now for over an hour, feel free to get up and do that. Okay. So technology, it can open many doors, particularly when vision loss seems to be closing many of them. And you are all probably very familiar with some of the non-visual low technologies, and they may have been part of your journey with vision loss. So for example, I'm willing to bet many of you have bump dots on something in your home, whether it's your microwave or a remote control. Somewhere you have something raised that you can feel and gives you a clue as to where your fingers are at. So bump dots are a type of low technology. That's kind of the gateway technology into vision rehabilitation, kind of a first step. But you've also probably noticed that using contrast, pulling out a white cup so that you don't over pour coffee into it, is another non-visual strategy that a lot of people will use. You also might be listening more so that you can hear somebody coming down the hall in your house, or you can hear when your cat is moving from one room to another. And you're just paying attention in a different way to the things that you're hearing. And those are all beginning changes that you start to make when your vision starts to fail. And at some point, I'm sure most of you have had more dramatic transitions or changes where you've had to go from one kind of technology to another. And that process may have been smooth, rocky, or somewhere in between. And with a changing eye condition, you're likely going to be facing more of those challenges as you go along. So I'm going to move on to Jim Denham, one of my colleagues, and Jim is going to talk about how computer technology can be addressed with changing vision and how you can keep connected using a computer regardless of vision loss. So Jim, I'll turn it over to you.
Thank you, Jean. I appreciate that. Welcome. Thanks again. I just want to add my thanks to those of you who are here, spending your afternoon with us. So I am the Access Technology Specialist with the Wisconsin Council of the Blind and Visually Impaired. And just full disclosure, I am totally blind, a little bit of light perception, but really nothing usable. So as we talk about some of this is technology that I use on a daily basis. So when we talk about individuals who are blind or visually impaired using technology, there are kind of two main areas that we look at. We look at using what vision that you currently have to access the computer screen. And that can be, changing the background color, changing the foreground color, magnifying the text to making it bigger, things like putting the mouse pointer in the center of the screen. And then for individuals such as myself that really, you can make the screen as big as you want or change it to whatever color, and we really can't access it. We're talking about using speech synthesis or screen reading technology to access this information. So having the computer actually speak information to you rather than you trying to look at it visually. So you're using that auditory sense rather than using that visual sense. And we talk about transitions. That can be a bit of a transition too, because you're going from traditionally listening, looking at a computer to now you're listening to the computer. So developing those listening skills and saying, hey, I'm not going to use my eyes anymore. So the good thing, it's not just a switch. It's not just something we go from one to the other. It's just a flip that switch. There's a couple different transitions that we can make. And the other significant development that's happened in the last 10 years or so is a lot of technology that allows us to, include some of these revisions is built into the technology you're already using. So it used to be if you wanted a screen magnifier, you had to go buy a piece of software or you had to do something. And now a lot of the operating systems that you're using have some of this stuff built in. So you can try some of this out and see if it works for you right away and just kind of try some different things. So I'm going to talk about Microsoft Windows just briefly, and then we'll talk about some other different devices and other different systems. So Microsoft Windows has a screen magnifier that's built into it, and you can access this. It's called the ease of access settings, and you can access this with Windows key plus U. So there's a lot. I won't go into the details of all the different settings that are there, but if you want to try some of this stuff out, you can try out the magnifier, and you can change the color and change the contrast and change some of this different stuff. And Windows also has something called Narrator, which is a screen reader built in. So if you say, hey, you try some of these different visual settings and they're not working, then you can actually access a screen reader that's built into Windows. And you can turn that on and try that out as well. And other devices have very similar options. So if you talk about a Mac, the Macintosh has the same. It's called Zoom on a Mac, or Narrator is a screen reader. A lot of mobile devices have this stuff is built in as well. So an iPhone has a screen magnifier and also has a screen reader. So this is built right into the operating system. So it's really nice. You can try this stuff out, see if it works for you. and give it a try. Now, these are just really basic options. We talked about, I like Dr. Gam's car analogy. These are really, basic things. These aren't the Trans Ams. These are maybe just the basic car models that you would use. So these give you some options. So for example, the Windows screen magnifier does full screen magnification, but it doesn't do some of the other things that some of the other options do. And so if we want to get, there are products on the market that will allow you to access additional features. One company that produces a set of products is called Freedom Scientific, and they are based here in the US. And they make a couple different programs. They make a program for screen magnification called Zoom Text. And Zoom Text, again, does the magnification. So it increases the magnification, changes the colors, changes the background color, puts your mouse pointer in the foreground. And it does a little bit more than what the basic Windows magnifier is going to do. So you can just try this out and see if it works. And if the built-in Windows doesn't work for you, the Zoom Text might be something else that's beneficial. For individuals who need speech access to a computer, Freedom Scientific makes a program called JAWS, which is screen reading software. So I'm actually a JAWS user. So as I navigate web pages, as I navigate emails, as I navigate documents in Word and Excel spreadsheets, it's reading that information to me. And JAWS does significantly more than the built-in Windows screen reader that's there. So the built-in one is great. The fact that it's there is I can turn it on any computer. It's really nice that it's just there. But I couldn't get by with just that. It doesn't read enough for me really to efficiently navigate the Windows operating system. So that is something that's for people who are just needs a screen reading. So you're going to say, what if I'm in the middle here? What if I, sometimes I need screen reading, sometimes I need screen magnification, or maybe I use screen magnification most of the day, but then at the end of the day, my eyes get really tired and I just want it to read to me. Well, the good news is that there's a product for you as well. So Freedom Scientific has something called Zoom Text Fusion. And Fusion is a combination of Zoom Text and JAWS. So you actually get both products, but you can run Fusion and you get the screen reading and the screen magnification. So for those who have tried screen magnification and it works for them somewhat, and sometimes it works, sometimes it doesn't work, and you're changing the background color, you're changing some of the different fonts, then it's maybe give Fusion a try, because it's a really nice transition. It's a way to say, okay, I'm not going to totally use speech. I'm not ready to give up looking at my computer screen, but once in a while, I want to try listening to my computer. So maybe I've got a long document I'm trying to read, or a web page I'm trying to read. And so Zoom Text Fusion was going to allow me to, turn on that screen reader when I need it and turn it off when it gets annoying. So the other thing I would say is, if you are using screen magnification and you want to start using screen reading, the listening skills are really important. Listening to what the computer is saying and understanding what it's saying is so very important. It can make that transition so much easier. It's kind of like driving down the street in a car and you're only seeing, every other signpost. Well, that's going to make it really difficult to navigate and know where you're at, because you might really miss something. So, understanding that speech, using those listening skills, developing those listening skills, again, is something that takes time. It's not something you do overnight, but it's something that definitely takes time. So there are some things out there for transition. There are some great, things. Try out some of these basic magnifications that's built into Windows or built into your Mac or built into your iPhone or your Android phone. Give them a try and see how they work for you. And if you need more, there are additional options that are out there. I think a lot of them are listed in our resources list.
Okay, thanks, Jim. I know a lot of us think we listen really well. I know I learned very quickly when I first started doing this job. I thought I listened well. And I tried talking books in the car one day, and I drove all the way to Platteville with it playing all the way down the road. Had no idea what the story was when I got there. So I had to learn some strategies for how to learn to listen. And that's what many people have to do when they make that decision that it's time to go from strictly visual information to visual plus auditory support to auditory only. Because you can be as productive with hearing things as you can with seeing things. It's a learning process. And I'm going to talk with you about some apps that are primarily used on smartphones or smart tablets. And smartphones are other devices that many of us have, and we only use a smidgen of the smartphone's capabilities because we don't know how to use the rest of it. And so using apps on your smartphone is a way to start figuring out the accessibility options that also exist on those smartphones. So any smartphone, whether it's an iOS or an Android, is fully accessible to someone with vision loss. And it can be accessible using magnification, and it can be accessible using screen reading. So if you use magnification on a cell phone, it's a small screen, remember? So it's no different than using a magnifier where you then have to learn how to scroll side to side and up and down in order to see everything that you want to see when you're gathering information. But there are lots of low vision assists that can make that smartphone much easier for you to use. You can also turn on screen reading. And so on an iOS device, as Jim mentioned, it's called VoiceOver, and on an Android device, it's called TalkBack. Some of the Android devices, you have to download the accessibility features in order to have them fully available to you, but they are fully available. And this also takes some learning. So never turn these things on and then walk away. Or if you're a well-intentioned family member, never turn these features on, hand it to somebody with low vision or no vision and say, go for it. Because the person's going to have a really, really hard time because it changes the gestures. And so always take the time, give yourself time, and be patient with yourself to start to begin to relearn the gestures and use the tutorials that are also available on your smartphones. They both, iOS and Android systems, have tutorials that can get you at least started on those. And one resource for learning how to do those better is Hadley, hadley.edu, and that will be on your resource list. Hadley has wonderful, short, detailed tutorials that can teach you how to use either an Android or an iOS smartphone better, and how to do more than just make a phone call, which is sometimes what we get stuck on. Well, it does my phone, but you have a computer in your hand and they can just do a lot more. So Hadley helps you get onto that learning curve to help you master some of these accessibility options. There are tons of apps available, and I'm sure if any of you have looked for apps for anything, there are just gobs of them available for any type of need. So I just have a basic PowerPoint just to give you something new to look at here. The thing about apps is that you can download a bunch of them and be disappointed in many of them. So look for a reliable place where you can find app reviews. And I'm going to give some on the handout for iOS devices. It's appleviz.com. And be with other people who have vision impairment, and that's also another good way to find out about a lot of these apps and which ones people are using to work for them. So having said that, let's look at a few. If I can advance my slides, there we go. There's the Hadley, a picture of their page. All of the Hadley classes, by the way, there's no cost to them. You work away at them at your own pace. Okay, there's been a lot of apps that use AI or artificial intelligence that actually are really good for a lot of different things. And the names of some of them are Seeing AI, Envision AI, Google Lookout, and SuperSense. And what these apps do is that they can read text in a lot of different types of texts. So you have the app on your phone or on a tablet, and you point your camera at text, you hold it above the text. It takes an image, and almost instantaneously it starts to read that text to you. So they all have different levels of text that they will read. Like they'll read short text, which is good for, like if you're sorting your mail, just tell you who the envelopes are from, whether or not they go in the round file or whether or not you have to attend to them. Then they will also read longer text, where they'll read a whole page. Like if you get a report from your eye doctor, or if you get any type of form, they'll also read that. So these are really good and inexpensive. So Seeing AI works for iOS, works with iOS devices. It's totally free. And Vision AI works with both iOS and Android devices. That one has a cost to it, $1.99 a month or $12.99 a year. Google Lookout, as its name suggests, works with Android devices, and SuperSense will work with both iOS and Android devices. But in addition to reading text to you, they can also identify money. They can tell you about colors. The color identifiers are not great, but they can get you in the ballpark at least. They can recognize people. They can recognize packaging. They can read barcodes. And again, the accuracy of barcodes is a little dependent on manufacturers putting barcodes into a system that these app developers have access to. So they can read a fair amount of things and give you lots of information without them being hard to use at all. So those are a couple apps that use artificial intelligence. But if you scan longer documents, or want to read things, file formats, and put them into your device in save devices so that you can retrieve them later, there is an app called a KNFB Reader. And this one's been around for a long time, but it's really an excellent app. It gives lots of information to you as you're trying to scan a page. And like I said, it's nice because you can scan 5 or 6 pages or 25 or 30 pages, or you can upload an instruction manual, you can upload a PDF file, and it will read any of those to you. So the KNFB Reader doesn't have the other bells and whistles that the AI apps have, but it is a good app for text reading. If you have low vision and still depend on vision for a lot of your reading, the KNFB Reader is able to manipulate the text. So it can make text bigger or smaller. It can change the contrast and font. It can change the background text color so that you can get it to look like you want it to look. You can also have a box that highlights as it reads so that you can follow along. So the KNFB Reader has a one-time fee that you pay to get the app, which is $99.99 in order to get that app onto your devices. And the KNFB Reader works with iOS devices, Android devices, and Windows 10 devices. Interestingly enough, the National Federation of the Blind, that NFB and KNFB Reader stands for National Federation of the Blind, recently made a very basic KNFB Reader available in their Newsline app. So if you are a Newsline user, you do have access without additional cost to KNFB Reader Basic. And Newsline, for those of you who don't know what that is a source of up-to-date news. So you have access to state and national newspapers. In Wisconsin, there's 15 daily newspapers that are read. They use synthesized speech, not human reading, but it's pretty good. You can also get national newspapers. So if you're a New York Times fan, you can get the New York Times read through Newsline. You can also get a bunch of magazines read, like Consumer Reports, New Yorker, Rolling Stone. You can also have breaking news sources through your newsline, like CNN and ESPN, emergency weather alerts, TV listings, and it will also read ads from major companies. So you can have in a newsline read the Target ad when they come out. So that has some nice features as well. And then there's a couple apps that will connect people with vision impairment to sighted people to give them information. And two of those, one is called Be My Eyes. This one is totally free. So when you open the app contacts some volunteer somewhere in the world. You aim your camera at something that you have a question about. When the volunteer comes on, you ask them that question. The volunteer will tell you where to put your camera so they can answer your question if they can, and answers your question. So you might be standing there holding a can and you don't know what's in that can that you grabbed out of the pantry. The Be My Eyes person could tell you if it's soup or beans or whatever. You might have trouble setting a digital display like ovens. And so you can make an attempt, turn on the Be My Eyes app, say, is my oven set at 350? And if not, they can direct you to where the up or down arrow is in order to get it at 350. You can also use it to help with clothing identification as to whether or not, what color is this shirt? Does it go with this blazer? In that volunteer's opinion. So Be My Eyes is totally free. And they're volunteers. And like I said, they're from all over the world. The Aira app and Be My Eyes is also for iOS and Android devices. The Aira app is also for iOS and Android devices. And this connects people with vision impairment with trained, paid professionals who provide visual information on demand. And so I'll tell you my current understanding of how you can access Aira, and Jim can correct me if I make an error here. But Aira is paired with businesses that will provide free use on the Aira app when you're in their business locations. So for example, Walgreens and Target are examples of where you can use that Aira app when you walk into Walgreens and you ask the agent to help you find the aspirin aisle. And when you get to the aspirin aisle, where is the kind of aspirin that you want to get? When you're done picking out your aspirin, they can direct you back to the checkout area. They can tell you if you're standing 6 feet away from the person in front of you. That agent stays with you all the while that you're in that business. The other places that have taken on the Aira app for people without cost are airports. So there's 45 US airports that were listed on their site that use Aira. So this is information with an agent talking you through from the time you enter that airport terminal till you get through security checks to your gate and onto the plane. Museums, also some museums. There wasn't a big list of museums, but some do use Aira app. And here in Wisconsin, the University of Wisconsin-Milwaukee has Aira apps available for anybody on their campus. So they've created this partnership, and when you're in that partnership, those partnership businesses or agencies or organizations, Aira is free to you. For use of Aira for other uses, there is a subscription fee, and those are monthly fees, and that's determined by the minutes that you're going to buy per month of that agent. And that can range, ooh, and now I forgot the low one. I forgot the low one for
$30.
Okay, because I know there was one that was 30, one that was 100, and then the big one was, what is it, $300 a month? So anyway, Aira is trained people and can stay with you until a task is completed. Okay, then for those of you who like single purpose apps, you know, sometimes single purpose apps are good. We all don't need a Swiss Army knife in one app. And so we have apps that just do some single things, and a real nice one that's again been around for a long time, but does a good job and actually does a better job than some of the AI apps is Tap Tap See for identifying objects in the environment. So again, you turn on your phone, aim it at something. It takes a little bit longer for this one to process the information because it's matching it to other picture images that are in its database, and it tells you what you're looking at. There are tons of GPS apps. Blind Square is one that I just put up as an example here. And the GPS apps, I really highly recommend working with an orientation mobility specialist so that you can choose an app that's going to best meet your travel needs and the routines that you have. If you're a walker or a bus driver or an international traveler, there are apps that sort of can fit those types of needs a little bit better. So at this point, I'm going to turn it over to Brent. And Brent is going to talk a little bit about entertainment and how to stay connected to entertainment that we all like to do.
Good evening, everyone. Thanks, Jean. Yeah, I get the fun part here, entertainment. So if you're anything like me, in the last number of years, you can be a little bit overwhelmed with all the different options for watching your television. So trying to figure out which way is best for you can be a little bit overwhelming. So I'm going to discuss a little bit about the different accessibility features and the different ways that you might want to go about watching your television. So pretty much these days, there's about 3 different basic ways that you can watch your television or get your programs. One would be the old-fashioned way through your old rabbit ears. There is still a signal out there. They have added more channels than there used to be than your basic 3 or 4. So you can get a few more channels that way, and it's going to depend on your area and the reception. And then you would hook that up to your television. And with that, it's a little simpler. You're only going to have a few channels you got to scroll through rather than 180 or 300 like some of the other cable options you might have. But with that, you're not going to have as many accessibility options. If you have a newer TV, there might be something in your television. If you go into your settings and then go into the accessibility portion of the menu, you can maybe make your menu a little bit larger, and you might also have an option to turn on audio descriptions. So if there are certain programs that have been audio described, and that's going to vary. So some of the newer ones generally have audio descriptions. The show that you watch will be described to you, the parts of it that you're not able to see. So let's say, for instance, you're watching a show and it's a cop and robber show and there's a bad guy that's hiding in the bushes. Audio description will describe to you that there's somebody that's hiding in the descriptions, something that you might not be aware of because you can't see what's going on. So most TVs, newer TVs have that capability to turn on the audio descriptions for that capability. If you want more channels and you go the route of a cable provider, so like the ones that are around here might be Charter or Time Warner, or Comcast. Those are some of the more popular ones, or even satellite companies like Dish. Then you're going to have more options for accessibility. One of those would be through your television remote. A lot of the cable companies now are starting to provide larger remotes. So if you do have some usable vision, you should be able to get a larger remote. And then a lot of the cable providers now also will provide audio feedback in your menus. So as you're scrolling through your cable channels, If it's activated, which you would do through your cable provider, you would need to talk to them to have them activate it. It will talk to you and tell you what channel you're surfing on. It will give you the channel. It will tell you what program is currently airing. And then if you're to scroll through, it will talk to you through all the different channels or all the different shows that you're scrolling through. The next option for television watching outside of getting a cable provider would be through using your different electronic devices to watch shows through different applications. So just like if you have a smartphone, that you would have different apps on your phone, you can also do that through your television program viewing. So this is a little bit newer, and they've come a long way already just in a few years. So one example of an application to watch shows might be like through Netflix, which is probably the most popular application that's out there. The great thing about Netflix is that all of their original shows that are produced through Netflix do have audio description automatically included with their programming. So if you go that route, you can use lots of different options to watch those different applications. You can get a smart TV, which is essentially like a computer that's in your TV, and then you would have all those different applications on your TV. If you get like an Apple TV or the Amazon television, smart TV, those automatically have voice back options in them. So as you're going through your channels, everything's going to talk to you as you go through it. If you get an Apple TV or an Amazon smart TV. Another way to do that would be to get a device that you would plug into your current TV if it has a USB port. So examples of that might be these days an Amazon Fire Stick, a Roku stick, Apple TV 4K that can plug in to your television. And so essentially what you're doing is you're plugging that in to your television, and it's going to bring up those different applications that you can watch. I should have mentioned earlier, like Netflix or some of those applications, you do need to pay a subscription fee for, but there are plenty of free apps that you can get for television viewing. The other thing that's now provided that wasn't before is that you can get a lot of your cable type television programs or your local type programs through that venue as well. So like if we were to use Hulu, for instance, which is a popular one, they have something called Hulu Live, where it has your NBC, your ABC, your CBS all included in that, along with other type of cable type stations like ESPN, A&E, a lot of the more popular ones. With that option, you're paying a little bit less than you might for your cable, like through Charter. If you were to get like Hulu Live, I think these days is around $60 some. Another popular live type of streaming is YouTube TV. They also have many different channel options. So a lot of it's going to depend on what your favorite channels are, the type of things you want to watch, as to what route you go for that. And again, you know, we're here to help. You know, if you have questions on what might be best for you, this is a lot of information, and with technology, there's a lot to take in. So we're always here to answer any questions that you might have. I should also mention the American Council of the Blind. Their website's www.acb.org. They have a list of all the different programs that have audio descriptions available. there's also, they also have a listing of a lot of other things there that you might find interesting. So like they have a list of different airlines that have, they'll tell you which airlines have audio description on their movies on the in-flight. Like I know United has most of theirs. What's another? American has audio description available on a lot of their in-flight shows. So ACB has a list of the different airlines. Another neat thing that's out there is, let's say you're watching an audio description show with your family, but they don't want to hear the audio description. So there's an application you can get downloaded onto your electronic device, like your phone, if you have a smartphone or a tablet, called Spectrum Access. And this only works for certain movies. It doesn't work for every audio described show that's out there. It's for just certain movies that are out there. But what Spectrum Access can do is that you download it on your phone, and once your movie starts playing on your television and you have it playing without the audio description, if you turn on the Spectrum Access app on your phone, the microphone will detect what's playing, and it will play the audio description on your phone. And then you could take like some earplugs and put them into your phone and then listen to it through your phone with the audio description while the rest of your family is watching the regular programming through the TV. So those are a few different options for television viewing and different ways that you can get your programming. So there's also audio described in the Madison area. Different live events also have that option. A lot of movie theaters have that availability in them. If you go and ask for a set of headphones with audio description, a lot of the more popular movie theaters have that available to you. If you go to events at the Kohl Center, a lot of times they will also have headphones available for audio description for whatever program is showing. The Overture Center also has that capability. I would always suggest if you have, let's say you're going to Hamilton or something, you spend a lot of money, to contact them as soon as you can and let them know you're coming, you're visually impaired, you'd like the audio description option available, because they'll actually have a live person that's there that will be describing what's going on the stage. So they need to have that set up. They don't have it set up for every show. They'll do it by request. So you need to let them know well ahead of time that you'll be attending a certain show, so they have that option available to you. So that's my portion of the program tonight. Again, feel free to contact me, the council, or the State Office for the Blind, which have different representatives pocketed around the state that can also assist. Thank you.
Thanks, Brent. Seems very nice to hear about Overture Center and the Kohl Center and flying on an airplane. So hopefully we'll actually be able to do that maybe by the middle of next year. You never know. All righty. So as mentioned earlier, you'll get info about all of these. We'll give you our contact list as well. Know that there are places throughout the state of Wisconsin where you can find services, and this is a list of some of them, and that will also be in the handout. Okay, so any questions?
So we're going to go into some more questions, but before we do that, I wanted to mention that we are going to stay on for a while, and Dave will be on for a while, and we'll go through some of the questions that have come through the chat, a couple of the questions that were asked in advance. But before we do that, since we're coming up on the time when we had talked about ending it. If you do have anything that you need to do, you should feel free to do that, but please feel free to stay on for questions. And then for both the council and for the McPherson Eye Research Institute, we do each have websites where you can find out much more, including the contact information for all of the people that have been on there on this. The council's website is wcblind.org, and the McPherson Eye Research Institute's website is vision.wisc.edu. And perhaps Jean can put all of our contact information on the sheet that she's going to send out to everyone as well. And you can certainly feel free to get in touch with me at the McPherson ERI if you'd like a copy of that calendar and annual report that Dave mentioned when he was talking. I know that many of you do get that anyway, and that is going to go in the mail. Might even be going in the mail now. I dropped it off at the mail house earlier today. And then I'll say that we do intend to do more of these over time, including probably one on age-related macular degeneration. So stay tuned for information about that. We're very grateful to partner with the council as well. Now, you can ask questions about any of the things that were spoken about or anything else that you have in mind, but I'll start off with a question for Dave. And Dave, you're going to have to unmute, but a couple of people in the chat asked about COVID and whether that has, how that has affected research going on now, and also whether there is anything to be learned from the research on COVID as far as viruses as vectors, for instance.
Yeah, so first of all, COVID affected everybody and the hospital and the research programs alike. For the most part, what happened was, some labs were designated essential, and they were allowed to continue at a reduced capacity. Generally speaking, that meant that you could continue to maintain critical experiments, but you could not start new ones. And that was for a few months. My lab was one of the ones that was deemed that, so we were benefit to that. And so we had, at that point, we were reduced to about 25% capacity. And then there were a couple of steps of rebooting the campus, and went up to 50% in May, and then a full 100% at the end of July. We still don't have undergraduates because I don't trust that they actually stay distanced and wear masks. So we don't have any undergraduates, but all my employees and staff have been back since the beginning of August. And so we really feel like we're at 95% capacity now, and have been since the late summer. Other labs are different in terms of what, and of course we have, 190 members in the McPherson Eye Research Institute, and a good half of the, probably 60 to 80 different laboratories. And so they're all a bit different. Some of them were forced to shut down more than others, but everyone is back online, maybe not at 100%. But the university here, I gotta give them a lot of credit. The university did a really good job of keeping everyone safe, but not, but allowing critical things to be maintained as long as we followed the rules. And it wasn't easy following. There was a lot of oversight, as there should be, to make sure that people weren't bending the rules. So the university did a great job during that whole time, and I'm very grateful to them. So overall, I would say we did much better. We were able to move forward much better than most universities. It also helped that at that time, it was not as prevalent here, say, as in on the coasts in New York and other areas as well. And then I think the other question was research directly regarding COVID. So we do have people within our organization that have virology experience and other expertise on campus that are not necessarily vision related. I think you might have heard that it is potentially possible to get viral infections through the surface of your eyes, because there are mucous membranes like the lining of your throat and your nose and things like that too. There's been described a low-grade conjunctivitis that has occurred along with COVID infections. I have not seen that here in Wisconsin, though, that sort of a presentation. And also, it's not clear whether or not that's actual active infection, because as you might have noticed, if you get a cold or you just get sick, your eyes get red sometimes. And so just because your eyes get injected doesn't mean that that's an area of active infection. So the jury's still out on that, but it makes theoretical sense to protect all areas that are potential gateways to viral infection. And one of those is the surface of your eyes. So nothing that I know of that's being done specifically for treatment of coronavirus on the surface of the eye, because it doesn't cause long-term damage that we know of, or any other issues. I do, interestingly enough, screen for patients who get what's called COVID toes. And those are when, because it's a vasculitis. So what COVID does is oftentimes causes damage to small blood vessels. And you can get almost kind of a gangrene and loss of, and pain and loss of your toes. They get purple and they get kind of nasty looking. And in some of those patients, they have gotten also vascular changes in their retina, which are asymptomatic, so they haven't lost vision, but does change the treatment regimen for those patients, because it's considered more systemic. So it's more than you wanted to know, but it's COVID, so people, it's always relevant.
The question was also, perhaps, is there anything from the COVID research that we're likely to learn that might affect the vision research?
Honestly, coronavirus is not going to be one that would be it'd be a hard sell anyway, but it would not be one of the viruses that one would deactivate to use to deliver genes. It doesn't have anything in particular with regard to advantages over other viral shells that are currently in use and already have a well-known safety tolerance. One way to think about it, one analogy that I use, because I love analogies, is you could think of a virus as an M&M, and the shell is what binds to and looks for cells that it wants to invade. And then the chocolate inside is the DNA of that virus that then goes in and wreaks havoc on that cell. Sort of like a Trojan horse. The soldiers are the chocolate and the horse is the shell outside. So what we do in delivery of genes that are good for you, so when we're trying to treat you with a good gene and not, is we take the chocolate out and replace it with something else, a good thing. Chocolate's good. Maybe it's not a great analogy. Like I said, I don't promise all of them are good, but so you remove that, but you use the candy shell as a means to get into the cell, because it's, how many millions of years of evolution and work that's been done to get that candy shell to be just really, really good at homing in and getting past all the defenses of a cell and injecting genes. So it's a way to commandeer that biological system.
Next question. Have you seen the Harvard Medical School study on epigenetics reprogramming? Would this be a potential?
Yeah, that was the one. And so that's actually, it's interesting. It was a Nature article that just came out, and essentially what they're doing is reprogramming cells to make them younger. So that would not help RP, because what they're trying to do there is just make cells less, like reversing aging, one of those things. And they did have vision as part of that, but it was ganglion cells. So it was not photoreceptors or RPE, which are affected in RP, but rather ganglion cells, which can tend to get older in glaucoma. And glaucoma is actually something that we also do at the McPherson Eye Research Institute. It's not the subject of this talk, but there is some thought that it may help with regeneration, at least in this case, in terms of retinal ganglion cells. It's very, very early sort of gee whiz bang sort of stuff that was done in mice and may or may not be. I mean, there's a mountain of things that were done that are kind of cool, things like that are worth looking into, but don't necessarily mean that they'll reach patient treatment. Plus, I will tell you what they're doing is they're using the same genetic manipulation that we use to make stem cells. And when we do that, we have to go to great lengths to show that we don't form tumors. So there is a significant risk that you could convert these. If you go too far past making them younger, you could turn them into what are called teratomas or tumors. So there's a lot of work to be done there. But like everything else, it's cool. It's a new avenue to explore. It's going to take years to work out. It may work out, may not. But the more shots on goal that we have, the better.
Next question. Do you have any observations on the Biogen license with Mass Eye and Ear relating to gene therapy and the PF31 gene?
Yeah, that's PRPF31 actually, which is a series of different genes that cause autosomal dominant retinitis pigmentosa. I answered Westbrook privately on that one. I didn't know how to do it for everybody. But yes, we actually work on PRPF31 here. We were part of the grant that produced IPS cells for the model system for Eric Pierce's lab at Massachusetts Eye and Ear Infirmary. So we were actually, UW had a role in the studies that were done to advance that research that was then subsequently picked up by Biogen. That's a gene therapy approach as well, but it's kind of a little bit different, and it's got promise.
Can you comment on microscaffolding? Is that technology mature?
Oh yeah, so that's what we've again, the Eye Institute here has pioneered most of that work. And that's in collaboration with Sarah Gong and Jack Ma, two wonderful engineers on campus. And so, yes, we had a very significant publication on that a couple of years ago. So we have another one coming out soon. And that goes back to when I talked about the challenge of not just making the spare parts, but delivering them in the proper orientation. So that's what we're working on to address that hurdle. But there's a downside to that. When you add scaffolds, when you add additional biosynthetic material, you're adding more stuff that then has to go through the FDA to make sure that those materials, which biodegrade, don't biodegrade into something that's toxic. So the more complexity you build into the product that you're putting into a patient, the higher the scrutiny, the more things that could go wrong too. So you want to take these in iterative steps. You want to do a pure biological product where we're just replacing cells, and then we can add to that as need be to improve the product over time. So yes, scaffolds are a big part of our program.
So this is a question that I think could go to people from the council or maybe Anne, to you as well. Dave, can you talk about night vision and other tools that can help seeing at night? I don't know who would want to field that first, but somebody's going to have to jump in.
That seems like more of a technology thing than, so certainly the gene therapies and the cell therapies that we're talking about are designed to save or restore rods, which provide you night vision. So that would be part and parcel of these therapies if they're aimed at rod-based disorders. But of course, that's not something you can go do right now. That's actually if you look at RPE65 in the Luxturna product, so the only gene therapy that's FDA approved for RPE65, what that gene therapy didn't really improve their central vision, the patients who got it. It improved their night vision. It improved their ability to navigate in dimmer environments. So that is one of the benefits.
And I think related, or the question is also asking whether or not there are technologies that will help with seeing better when light is dim or night. And there are no good ones that can make that happen. Some people will wear contrasting filters, yellow sunglasses, orange sunglasses, that help them see better at dusk and dawn. But when the light's gone, the light's gone. And there's not really any technologies that change that substantially.
We've got maybe 2 questions left, but before we get to those, I want to turn this over to Denise to kind of formally close us out in case anybody needs to get going, and then we'll stay on for those couple of questions after. Denise? I want to make sure you unmute. There we go.
Yeah, Michael, thank you so much. I wanted to just do a formal close so that if there are some of you who have little ones at home or dinner is calling your name, you can feel like you can comfortably step off. And if you want to continue the conversation, you can feel free to do that as well. So I just want to end our time together by thanking folks so much for spending these couple of hours. This was so informative on both the research and on the strategies. And I'm so grateful to everyone who presented this evening for sharing your time and your talent and your kindness with everyone. So on behalf of the council, I want to say thank you so much to the McPherson Eye Research Institute, and thank you so much to our staff and to each of you for choosing to attend.
Mm-hmm.
Yep, I couldn't agree more. We have a lot of very knowledgeable people on this call at the council, and it's interesting to hear about all of this. So let's get back. We've got one or two more questions, and then we will let everybody go. But they actually have gone through all the questions. We did have one that was sent in advance. Explain the cause of central visual distortion versus visual field loss as RP vision loss progresses from the outer edges inward. And I think
there's a couple of ways that can happen. One is that that piecemeal. So, again, vision starts with those photoreceptors recognizing photons of light and firing. So the photoreceptors don't necessarily deteriorate and die as a continuous wave. They'll go in patches. So you can have this puzzle-like loss of vision. But the center is cones, right? Mostly cones, and the very center is only cones, whereas the rods are on the outside. So if you have a rod, a mutation that only affects rods, you lose the periphery, but the central stays there for a while. The question has always been, why don't you keep the center forever? Because if the gene mutation is only in the rods, then you should be able to keep that center. As it turns out, there are things that the rods do that are necessary for the cones to stay healthy too. So you secondarily lose the cones after the rods go away. So that's the secondary portion of it. Now the distortion that you get can be from those cones starting to die in a piecemeal fashion, or in some cases of inherited retinal degenerative disease, you'll get swelling and called cystoid macular edema. So the retina won't stay compact, but will start to have fluid pockets that will appear. That stretches and distorts the retina. And when you do that, and the photoreceptors get out of their alignment and start to move apart, then the brain doesn't know where they're at. And so you see an object, but the brain thinks that the nose is here and the ear is over here, and it moves it. So the registration between the retinal receptors, the photoreceptors, and the brain starts to get thrown off. So usually when I say if there's distortion in RP, then we start to look to see whether there's cystoid macular edema or CME, because there are some drugs that can be used to try to get rid of that fluid and improve that metamorphopsia, which is a big word for distortion.
Mary, did you have a question or a follow-up to that? Sorry, Rosemary, I see that your hand.
Oh, hi. Yeah, can you hear me? Yeah, so the CME is the approach that we're taking right now with my eyes. But what was the other thing you had mentioned, that there is this function between the cones and rods what will be the other reason?
I've heard other people say that distortion just based upon the loss of, the slow death of the cones. So, that patchwork sort of puzzle piece is starting to be. So people's definition of distortion is different, right? Some people's distortion is straight lines are squiggly. Some people's distortion are straight lines have missing parts. And so those are kind of technically two different mechanisms. But normally when we as physicians or ophthalmologists talk about distortion, we think more about straight lines being wavy. And that's more of the CME.
I totally appreciate your metaphors. Your presentations have gotten better and better and better over the years.
By the time I'm 103, well, they'll get worse by then. But
they're really good. No, thank you.
So Dave, we have a question, and I think this is much too big a topic to go into now, but we'll probably do a separate talk on it. What is the latest research regarding macular degeneration? But I just want to know if you wanted to briefly say something about
Well,
that.
I'm assuming what the person means is age-related macular degeneration, which is adult onset, so after the age of 50, which is not a genetically, well, it has genetic risk factors, but it's not a genetic disorder like RP is. There are macular degenerations that are inherited. That's the Stargardt disease and Best disease that I mentioned earlier, the inherited macular degenerations. Sometimes they get lumped together. Now those are genetic, and those do have, in fact, we're working on both of those right now in my lab, one with a company and one with actually a family that's was on this call. But I'm assuming you mean age-related macular degeneration, and that, of course, affects millions of people in the United States, and we will have an entirely separate, at some point in 2021, we will do an entirely separate program on that, because there is a great deal going on there, and it would fill up a couple hours itself. And we'll do that with the Wisconsin Council.
And then I know this is not, again, also not on inherited retinal diseases, but may apply to some people on the call. So last question, somebody asked about a cataract removal, small cataracts that were removed, and is now having trouble in bright light. Is that characteristic, or could that be something else?
So it brings up a broader point, which is people who have RP can have other vision problems too, right? I mean, so just because you have RP, you still get cataracts. You could get glaucoma. You could get macular degeneration, age-related macular degeneration. So that's why it's important to continue to see your eye doctors, because you might just chalk it up to one thing, and in fact, you may have another. Take, for instance, glaucoma usually robs you of your peripheral vision. So let's say you have Stargardt disease. Well, you need that peripheral vision. That's what you're using to ambulate with and to get around. You don't want glaucoma, you don't want ticks and fleas and have them start taking away the peripheral vision. So it's important for you to continue to be evaluated for that. And you might chalk up a worsening of your RP when it's really cataracts. Now, I will say that cataract surgery in the setting of RP is something that you want to go to a professional who knows how to do that, right? Somebody who's familiar with doing cataract surgeries in patients with RP, because there are special considerations for that, as well as with macular degeneration. You want to know that you're doing it for the right reasons, because it's a surgery like everything else, and although it's the most common surgery done in the United States, there's still potential side effects to that. Now, getting to the comment about bright lights being a problem, that actually happens to everybody that gets cataract surgery. That's why you watch people with cataract surgery with those big old slee stack, never remembers Land of the Lost, those big slee stack sunglasses, because you go from having a cataract, which essentially is like a diffuser, something that reduces light and color. So, and then you go automatically with this, your windshield is clear, and you're like, oh my goodness, this is too much light. Pretty colors, but I can't take it. And it takes a while for your brain to get used to that. So I don't know how long ago you had cataract surgery. Some folks remain sensitive to light for the remainder of their life, and they just have to treat that with sunglasses and things like that. A lot of folks do get used to that over time.
Kathy, I see you had your hand up. Do you have a question or a follow-up?
I have a question. It's not really with COVID and having to wear a mask, and I have macular degeneration, and I only see out of one eye. Do you have any suggestions? My glasses fog up, and I can't see where I'm walking. Do you have any ideas?
Tape the top. I'll tell you what I do in the operating room. I tape my mask. You tape it. So when I'm operating and I'm wearing loops and I have to wear a mask, since I was a wee tyke in medical school, it would fog up immediately. If you just take some paper tape and you tape the top of it, you're good. It all goes down, not up.
So you put it
on your skin. It's got to overlap the mask onto the skin of your nose and the bridge of your nose and off to your cheekbones. Just play with it.
Okay, because it is so frustrating. And I said to the eye doctor, I want to throw my glasses across the room.
Oh, don't do that. But invest in some paper tape. You can get that at Walgreens. They use it for bandages and stuff. It's much more gentle for your skin. If you use kind of plastic tape, it has a lot of adhesives. And if you're like me and you've got kind of, cheap Scandinavian Irish skin, then it'll rip, it'll do a number, and you'll have a red nose for a long time. So
Okay, I'll have to try that paper tape. Okay, thank you.
I'm sure that many of us who wear glasses have noticed that as the most annoying thing of the onset of winter, walking into places with our glasses.
And it's hard when you can't see the city bus coming and you got to take transit to get to work.
Right.
Well, Kathy, you're too young to have age-related macular degeneration, so you must have Best disease or Stargardt.
No, I have. Thank you that I look young, but I do have age-related macular degeneration.
All right. Okay.
Mary?
I was just going to say, they have a spray that you can treat your lenses with to reduce the fogging on your glasses lenses.
Hmm.
Yeah, I think it's the same stuff they use for goggles for swimming. I don't know how long it lasts, but that's another thing.
Yeah, I don't know either, but I was thinking of getting some, but I like your idea about the paper tape too. That makes sense.
It works. I can promise you it works.
Mm-hmm.
It does.
Well, I think we've gotten through all the questions, and if I've missed any of your questions, I'm sorry, but do feel free to get in touch with us. You can get in touch with Jean at the council or with me at the McPherson Eye Research Institute, and you'll receive information about that.
I just had one other thought. When you mentioned about night vision, they do have, I saw in one of those expensive catalogs, the Comic or Schlemmer, they had a night vision device. And I was thinking too, it's like, wow, does somebody have an app that would work like that, where you could, actually produce that night vision effect where you could see, even with your limited field, but it would give that effect. But you guys at the WCB, you don't know of any devices or apps that do that, do you?
I don't, sorry.
No.
I have a couple hunters who use night vision goggles who have low vision.
Yeah.
That seems
send them the link. I'm sure they'd be happy to take a look at it.
Yeah, it's actually a little handheld device. So I'll share the info with you.
Yeah, thanks.
Sure.
Well, thank you all, and thanks to everybody from the council. They do great work, and we will see you again for the next sessions that we do.
Yeah, this was great fun. Thank you for spending the late afternoon, early evening with us, and thank you to the Wisconsin Council.
It was
so fortunate, I got to say, to be in this state. Every state does things a little bit differently, and every county sometimes does things a little bit differently, or a lot differently, as Jean will tell you. We are in a fortunate little corner of the world with the services that we have and the people who care as much as they do. And I think it just mirrors the quality of the people we have in the state too. So maybe that's just what it is. But thank you all very much.
Thank you for all your research in eye diseases.
Oh, I know. Thank you. That's what we do. And it's not just me. All you hear is me talking, right? But there's
your staff.
There's an army of people that work on issues that are related to the folks on this call. I just get to sit up here and wear an uncomfortable jacket and talk to you about it. But it's not all me by any means.
Well, tell them all thank you.
Yeah.
You know what amazes me? What amazes me is that you guys that are slaving away in the labs and everything, you don't actually have the disease, but yet you can describe to us to a T what it's like.
Yeah. Yeah.
Well, the benefit is I listen to Marshall Flax and the folks from WCBVI that we get to interact with, and I listen to patients.
Screen up there
of seeing folks and the folks that go to.
That's how it works. When one talks, then it comes back to their.
Yeah.
Yeah, and then I have the pleasure of knowing a lot of you, and getting to understand your triumphs as well as your struggles. What amazes me and what I tell parents, first and foremost, is first of all, I mean,
they might have it muted.
It's hard to get the diagnosis, but I am constantly amazed at the things that people do with the challenges that they're given. It's devastating sometimes, especially for parents when they try to project their own lives into the eyes of somebody who may not have normal vision. And I just say, you just watch and see what your child will do, because that child will they may not be an airline pilot, they may not be an ophthalmologist, but don't count them out for anything else. So with good services and a good positive outlook, and this group here is just a shining example of that.
Well, it certainly takes away the isolation of feeling like you're the only one in the world, that has it.
Absolutely.
People care. All right.
Why isn't still? Hi, David.
Hey, how you doing?
Good. How are you?
I'm doing fine. Saw lots of familiar names. So
Tim,
Good
are you
job.
staying- are you staying in
Michael.
shape? Are you staying in shape to bike over the winter?
Oh, absolutely.
Okay, good. We're going to do something. We're going to send out
we're
information.
gonna make it Cycle for Sight Plus. So we're gonna let you do what you want to do.
Awesome.
All right, and you'll have more information from Michael and myself on that later. You guys all take care. Have a wonderful evening, and thanks again.
Thank you.
Thank you,
Happy
guys.
holidays.
Take care.
Bye.
Bye.